Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College in the UK, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view of the scientific community regarding the challenges and opportunities that will come with exascale computing, especially for computational fluid dynamics and the study of turbulent flows. So this podcast is part of the ExCALIBUR initiative, which is the UK answer to the transition to exascale computing. It is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is mainly to develop a new generation of software for the exascale era. So this podcast is also part of the UK Turbulence Consortium. And I'm very pleased to say that today we have an international guest from the US. It's Professor Jesse Capecelatro from the Department of Mechanical Engineering at the University of Michigan. His research interest is broadly in computational fluid dynamics, high performance computing, multi-phase gradular flows. He has been doing some work recently around COVID-19, so we are going to be discussing this with him. So good morning for you, Jesse.
Yeah, hello, good morning, and it's a pleasure to be here. Thanks for having me.
Great, thank you very much. So I know you have been extremely present, I will say, with on Twitter and on giving some presentation for GFM and the CDT in Leeds. But can you briefly tell us a little bit more about yourself, where you're from, what you have studied, and how did you end up at the University of Michigan?
Sure, yeah. So I grew up in New York, about an hour north of New York City, a suburb. And yeah, I was sort of, broadly interested in math and science. And so I decided to, let's try engineering. And I went upstate New York, Binghamton, which probably most of you have not heard of, but it's famously one of the probably cloudiest cities in the country. And after 4 years, I did my undergraduate in mechanical engineering. I got the opportunity to do a summer research program doing related to renewable energy and biofuels, and so I got really hooked on renewable energy, and that was my first introduction to research, and so I decided I'm going to do grad school, and I was at this sort of crossroads. Do I want to just do a deep dive into renewable energy, or it quickly became apparent that fluid dynamics and turbulence, and becoming an expert in that area would open the doors for not only renewable energy, but other applications as well. And I thought, instead of pigeonholing myself into a particular application, I wanted to more broadly study turbulence. And I was very interested in computational work. I did a lot of, in middle school and elementary school, I was the first person on my street to get the internet. It was kind of funny, how, I'm 33 years old, but it seems like a very long time ago when we didn't all have the internet at our tips of our fingers. And so I got really into HTML and creating websites, and I think that was sort of my gateway into programming. And so I went to graduate school, master's at University of Colorado, and 2 years later, my advisor told me, "Hey, I'm moving to Cornell." So I said, "Okay, I'm going back to New York." I met my wife there, so it wasn't, Colorado is great. I wanted to get out of New York and be in the mountains, but I was happy to go back. Finished my PhD at Cornell in mechanical and aerospace engineering. I spent around that time, started working with Rodney Fox from Iowa State, but he also spends a lot of time in France. And so I spent 2 summers in École Centrale Paris, doing multi-phase flow and turbulence modeling. And then I did a postdoc at the University of Illinois. I wanted to kind of move away from multi-phase flow a little bit, and that introduced me to compressible flow and combustion. And then I joined Michigan about 5 years ago in 2016, and since then I've been sort of bridging that gap, bringing my PhD work with multi-phase flow, my postdoc work with compressible and reacting flows, and so now a lot of my work today is on high-speed or compressible multi-phase flows, which is exciting and challenging, and there's a lot to be done in that area.
Great, thank you very much. So you said you have been working at the University of Michigan for 5 years or so. So my next question is, I'd like to know what's the best thing about your current position. what do you really like about working for the University of Michigan?
Yeah, so the University of Michigan is in Ann Arbor, and Ann Arbor is a really fantastic little, I wouldn't even call it a city. I grew up near New York, so I by no means call it a city, but there are folks who might call it a city. It's just a great place to live. I like the climate. There's nice hiking. My wife and kid and son are going up to the UP to go backpacking. It's just beautiful up there. So I'm glad that we landed here. I like the area. But in terms of my job, I've been lucky enough the last 5 years to work. Everything we do is computational and turbulence, and most of it's multi-phase. But I've had the opportunity to do work with NASA, and I'm sure we'll talk a little bit more about that, with plume surface interactions. So trying to land spacecrafts on planets, multi-phase flows is a large challenge. And then for COVID-19, the variety of different projects I've been able to work on has probably been my favorite part of this job. And then on top of that, we just have really, really good students. And so, being able to work with just a fantastic team has been wonderful.
Great. So, so I know you have it's called the Multiphase and Multiphysics Flow Lab. So this is your research group. So can you briefly tell us a little bit more about the research activities that, I mean, you already talked a lot about what, but if you can, give us an idea of what you're doing.
Yeah. So essentially, we have two in-house research codes. I think it's good to phrase it that way. We have sort of a purely explicit, compressible flow solver, and then we have our low Mach number flow solver. And so we look at, with those two codes, we look at, with the high-speed flow solver, a lot of numerical method development and algorithm development in order to simulate particles in the presence of shock waves and turbulence. And so we have a mix of development, but also looking at physics of those types of flows. And that's mostly funded by NASA these days. And so there's essentially, NASA has recognized that plume surface interactions is really one of the greatest challenges for future missions. And anyone who has watched the Perseverance mission, the landing back in February, you might be familiar with they use what's called the sky crane maneuver. So essentially, the sky crane was hovering 20, 30 feet above the surface of Mars and lowered the rover. And the reason they did that was because they didn't want to get the exhaust plumes too close to the surface, because what happens is you end up fluidizing the surface, ejecting material, creating craters. And so the sky crane is sort of mitigate that. But even hovering 30 feet above, you can see, we were able to see in the video rocks getting ejected. InSight a couple of years ago did the same sky crane maneuver and had a wind sensor damage from the ejecta, right? And for future missions like sample return or eventually sending people to Mars, you can't, sky crane's not an option. You have to get the spacecraft right to the surface. And so there's been this large effort by NASA to try to come up with, improve their numerical models because experiments under the low atmosphere and gravity conditions is very challenging. So that's been a big effort. But then at the same time, I've been very much extending my work for my PhD, looking at like fluidized bed type of systems for energy conversion. And so that's been using our incompressible flow solver, and that involves heat and mass transfer in dense particle suspensions. And a lot of what we're interested in is turbulence modeling. When you scale up, usually what people do when they design these reactors is typically make assumptions of well-mixed, uniform mixing, but really we know that there's, fluid dynamics is complicated, there's three-dimensionality. So how do you incorporate that to reduce order models? And so one effort is using machine learning data-driven approaches, which I argue for multi-phase turbulence, it's the perfect playground to test these new ideas for machine learning. And then at the same time, we have a project from the Navy to look at dust ingestion. So that's been an opportunity to look at fine particulates where you have electrostatic interactions and van der Waals cohesion playing a role, again, in turbulence. And so how do you reconcile all those scales, turbulent time scales and length scales, all the way down to the van der Waals interactions? And then all of that's multi-phase, but we do a little bit of combustion, developing adjuvant-based methods for sensitivity and optimization. So So we have this umbrella of computational fluid dynamics and turbulence, but we're applying it to, I think, a variety of exciting different applications.
Excellent, very good, thank you. Before we talk more about numerical methods and Exascale and everything, can you tell us more about, I mean, you said you have been very active in studying the COVID-19 propagation with simulations of droplets during, you know, expiratory events. So can you tell us a little bit more about everything you have done around the COVID-19 research?
Yeah, so we've sort of had two thrusts in the area. Right when the pandemic started, I mean, this was, oh gosh, February of 2020. So this is before COVID-19 was coined. You know, there was an email sent out to the College of Engineering from a doctor at the VA hospital near our campus saying that, hey, there's SARS-CoV-2, whatever they're calling it at the time. There's some concern about it because of what's happening in China. And so their preferred method when patients come in is to use this high flow rate heated nasal cannula, right, to give patients oxygen. And there's a new policy in place saying they were worried is going to lead to aerosolization. And so what they wanted, so they're requiring the doctors to intubate patients, which has a lot of risk and they didn't want to do. And they asked, can anyone help? And when I saw this email, I thought, well, you know, I'm a fluid dynamicist and I do stuff with particles. And if there's ever a time where I can actually maybe make a difference, like this would be now, and it'd be silly not to respond. And so I put together a team of fluid dynamicists at our university. We have a number of really talented and excellent folks who do CFD and experimental fluids here. And it quickly became apparent that, you know, we need to meet with the doctors and figure it out. And so that was my introduction. And since then, I've been working very closely with folks who usually do combustion experiments, particulate measurements. We're using that same equipment that they use for detecting the particulates from emissions for aerosol detection here. And so we brought it to the hospital, measured the aerosol, and they changed the policy. I mean, it was usually it was, we did this within 2 weeks and they changed the policy. It was amazing. And since then, we've done work on the campus buses to measure transmission and look at coming up with policies. The whole bus routing system changed to make sure the routes were less than 15 minutes, windows open. We've worked with the School of Dentistry, and now we're working with the college to help reopen in the fall, looking at transmission in classrooms. But I would say, you know, we see a lot of studies coming online of CFD being used to look at aerosol transmission. And usually that's useful for that particular application. What I'm very interested in right now is you know, we're working with risk analysts. And as a fluid dynamicist, we usually think risk is transmission, but that's not the case. You know, the risk is someone going to go to the hospital and be severely sick or die? And transmission is the very first element of that, right? And so what's almost entirely done is you assume well mixed, you use some Wells-Riley or well mixed model, and then you plug that into a dose response function. And so what I see the role of CFD is to tell us, well, in reality, rooms are rarely well mixed. Can we really quantify how poor would a well mixed assumption be? And can we correct these models? Because when you do risk assessment, you have to run these models thousands and thousands of times. So we can't do CFD every time. And so right now I'm very interested in looking at how can we improve these well mixed models to incorporate a locality, the idea that, you know, on average, well mixed might be okay, but it's not going to tell you about the transmission or dose of individuals in that space. And so that's what we're focused on now.
Excellent. Thank you very much. It was very detailed overview of your research activities. And I'm glad to see that policymakers are listening to you and are changing their policies according to.
Well, locally, and they are.
Well,
I'd say at the local level, they're very interested in hearing about the science, which is great.
It's a good start. Right. Let's talk a little bit more about your the numerical tools that you are using. So I know you are using a code called the J code. So can you tell us a little bit more about the J code? I mean, What numerics are you using, parallelization strategies, and so on and so on?
Yeah, so J-code, I mentioned we have two in-house codes. J-code is the compressible solver that I started developing when I left University of Illinois for my postdoc. And the idea was I was bringing in a lot of the multi-phase flow algorithms I developed previously during my PhD into that flow solver. And at the time, it just became apparent it's not as easy as just taking what's been done for incompressible flows and bring those models into a compressible flow solver. But in a lot of ways, J-code is pretty standard in the sense it's a structured code, it's curvilinear, it's purely explicit, high order. And my philosophy has always been I want, there's a couple ingredients I want in my research code, and I hope to make it clear that when it comes to compressible turbulent flows, the move towards exascale or the future, it's not yet. I don't think it's very much figured out in a lot of ways. And so for my philosophy, I've always wanted a code that's highly scalable, that's high accurate, and robust. Robust in the sense we don't have to tune artificial dissipation. That's usually not something you worry too much about for incompressible flows, but for compressible flows it very much is. And so I very much like structured meshes. There's very low overhead. And so how do you reconcile structured meshes with complex geometries? We very much made use of inverse boundary methods. And I think inverse boundary methods for incompressible flows is pretty mature. We know that there's cut cell methods, direct forcing, and we've seen a lot of success. For compressible flows, it's much less mature, and there's been a lot of focus on that in very recent years. But I'm a big believer in structured code that has very nice parallel performance, and then use inverse boundaries for the complex geometries, and just have something that scales. And so that's sort of the idea. But what's becoming more and more apparent is simply solving the conservation equations discretely is not enough. So conservation, mass, momentum, and energy is great, but it's becoming more and more apparent that conservation of secondary quantities is essential, meaning conserving kinetic energy and entropy, for example. And that's really necessary for robustness and stability, especially in the presence of shock waves. And that's where I think things become tricky, because we use a high order finite difference that satisfies the summation by parts properties. And so that has nice energy stability properties. So it's essentially centered finite difference, high order. And then near the boundary, the stencils get modified in order to ensure an energy estimate. But that doesn't give you local kinetic energy conservation. So on top of that, we do you could do split the convective term to ensure that you get kinetic energy preservation. And people have been doing that for years, and we see that helps a lot. But still, that's not enough when you have, the flows we care about tend to be turbulent and have shock waves. And so that just, how do you simultaneously have the resolution and the high order accuracy for the small scale structures, but also avoid Gibbs phenomenon and overly dissipative near the shocks. And I don't think it's clear the best way to do that yet. So we've been using kind of shock capturing methods to add local artificial dissipation near shocks, which works really great unless you have shocks, steady shocks, because that will introduce some Gibbs phenomenon, and if your shock is steady, that'll grow in time, and you'll get very oscillatory solutions. And so what you really need there are entropy stable schemes. And what it seems like to me is using a finite difference like scheme with kinetic energy and entropy stability is kind of like fitting a round peg into or a square peg into a round hole, right? And I think this is why you're seeing a lot of talk about DG, like finite element methods naturally get some of these properties. But when you have turbulence, DG faces these same problems. And so it's very much not obvious what the path forward is. But whatever the path forward is, like I said, I want to have a scheme that's highly scalable, low dissipative, and high accurate, and robust. And it's easy to get 3 of those. It's very hard to get all 4. So J-code is built on those ideas, but then on top of that, we do multi-phase flow. We make use of inverse boundaries to do particle resolve calculations, but then we also use Lagrangian particle tracking with two-way coupling and collisions, so four-way coupling. That's not, that's pretty standard for incompressible flows, but extending that to compressible flows, I didn't realize when I joined Michigan, I thought, let's just do the Euler-Lagrange modeling and a compressible flow solver. And you quickly realize, you read 10 different papers and you see 10 different sets of equations. So we went through the exercise of rederiving the equations and so forth. And so, yeah, we routinely do simulations with tens or hundreds of millions of particles that attract individually with momentum and energy exchange. So that's sort of the flavor of that code.
Okay, thank you. And just for the people who are listening, is it written in C, in Fortran, or?
Yep. So this is Fortran, and the reason being is, I think it's just legacy. My advisor during my PhD wrote his code in Fortran. It was based off of legacy code from Stanford, and so I really like Fortran quite a bit. We're starting to very much Fortran 90, but we're starting to embrace sort of the object-oriented Fortran 2008 stuff as well. So yeah, and that's all MPI. And again, I said structured curvilinear for J code, and so we make use of just a standard domain decomposition, which gives us, it does what we need, because we don't have to worry too much about load balancing in that sense.
Excellent. And final, I'm very curious. So you said you are using high order finite difference. Are they explicit?
Yep. Yeah. So
everything is explicit.
This code is purely explicit. We do use some when we do the particle communication to the fluid. Yeah. We do it in a way that we decouple the particle size from the mesh. So a standard approach would be you would extrapolate to the grid, or you do particle and cell, but you can't get grid refinement under that case. So if you have refinement near a wall where you have a large particle size distribution, those tend to break down. So what we do is we send the particle data to the grid in a way that couples that through a filtering process, and that's done implicitly. But everything else is explicit, which is the reason I do that is because we want to resolve the acoustic timescale for most of our problems. And so the code is just very fast. Purely explicit, very, very fast.
Of course. Great. And maybe I missed that, but you do not have any issues with load balancing when you're dealing with particle-laden flows?
So a lot of the flows we tend to look at are turbulent, and particles tend to be everywhere.
Okay.
And so that's not too big a problem, but we are looking at some cases of we're very much with this work with NASA, looking at high-speed erosion. And so there's been a lot of nice work done on the scaling of you have a bed of particles in a water flume and looking at the erosion. We're looking at the same problem, but now it's Martian conditions, right? And so now what's the erosion when you have a Mach 1 flow and your density ratio is 300,000, And so in that case, all the particles are on the bottom of the domain, and if simply decomposing in 2 directions instead of 3 works fine. So we haven't had to worry too much. But we are working with another group to do towards exascale computing, to do combined GPUs and CPUs and spectral code. And it might, depending on how we do the parallelization, we might have to think more carefully about how to do that.
Great, thank you. I have another question. It's about Ron's closure models. There's a lot of model designed for single phase turbulent model, but can you tell us a little bit more about your work on Ron's closure for multi-phase flows?
Yeah. So what we see a lot these days, over and over, different machine learning techniques for Rand's closure, right? And a lot of it is motivated for flow separation, where classical methods tend to break down. But for single phase flows, a lot of those approaches tend to take existing models and then augment them or correct them. The challenge with the type of multi-phase flows we look at, where it's the coupling with the particles that induce the turbulence, you get fundamentally new unclosed terms. We get what we call drag production. So this is purely a generation of TKE, turbulent kinetic energy, through the drag exchange. And there just isn't any single phase model you can use and correct for to model that. So you have to start from ground zero. And so the approach we take is you can't simply just Reynolds average Navier-Stokes and come up to your multi-phase RANs. It's because you're going to have a small number of unclosed terms that just has a lot of complicated stuff going on in there. And so what we do is we derive an intermediate set of equations through volume filtering, which essentially looks like Navier-Stokes with volume fraction terms and drag. And then we Reynolds average that. And now the unclosed terms that are left over have correlations between volume fraction and velocity and unclosed drag. And so now it's just it's more interpretable. You know, we have more terms to close, but we have more physical meaning to those unclosed terms. But the challenge is the dimensional space is huge, right? So for a given Reynolds number, you change the volume fraction and the flow completely changes, right? And so we've been, I guess, I started looking at this towards the end of my PhD, and it just became apparent it's a very difficult problem. And so since joining Michigan, I've had one of my students, Sarah Beetham. She was very interested in sort of these data-driven techniques. And we decided not to use neural networks, which is, I think, the most popular approach these days, because we really want an approach that gives us, one, we can embed physics into. We want our models to be conservative, or invariant, and so forth, which there are new techniques to do that with neural networks. But at the same time, we didn't want this to be a black box. We want to come up with some nice algebraic expression for the individual terms appearing in equations. And so the approach we've taken closely follows the Cindy approach by Steve Brunton. The idea is you formulate the closure model in terms of, it's as an optimization problem, where you have an L1 penalty, which allows you to not just fit the data exactly, but it makes sure that the model is sparse, so that, which is useful in two ways. One is you get a model that doesn't have a million terms, it just has the important terms. And the second is through the optimization, you can start to see, okay, I think my model should be a function of these 10 different parameters. And through the optimization, I'll tell you, well, these ones don't matter at all. And these ones are very important. And so you can start to get an idea of the underlying physics of what's important to get this right and what's not. And so that's a technique we've used. So far, we've really applied it to homogeneous, sort of moderately dense suspension, and it seems to be working quite well. And so the idea is to, let's look at more complicated flows like with heat mass transfer or channel flows, for example. But this allows us to not rely on taking existing closures and correcting them, but just start from ground zero. But it does involve input from the user. You have to know something about the physics. You have to provide these tensor bases. And so, which I think I see the feature. You should have some input on what the corresponding physics is. But there are some ideas to relax that using other approaches like gene expression algorithms. So you don't have to come up with all of the basis functions yourself. But again, like I said, I think multi-phase turbulence is the perfect playground to test these newer data-driven techniques.
Great, thank you very much. Let's talk a little bit about Exascale. And there's a question that I always enjoy asking is, if tomorrow I give you an Exascale supercomputer, and assuming that all your solvers will be able to use it efficiently, what will you be able to do that you currently cannot do?
Yeah, so the first thing that comes to mind, and I guess I'll provide a little context first. The work we're doing with NASA involves a two-phase flow that's it's transonic, so it goes from subsonic to supersonic, and has volume fractions, particle loadings that go from very dilute, so the particles that get ejected are basically very, very dilute concentration moving at very high speed, all the way to the densely closed pack. So you get volume fractions spanning dilute to dense, very high Reynolds number, and a range of Mach numbers. And we don't even have drag laws that exist over the range. We just don't. And so if I want to run an Euler-Lagrange simulation, I need a model for the drag. It's also becoming more and more apparent that the the multi-phase flow community calls pseudo-turbulent kinetic energy. So that's going to be turbulence induced between particles. It's induced by the particles. That plays a big role, especially on some of the gas dynamics. If you have a shock going through a dense suspension of particles, it'll choke as it leaves. You could think of it as almost a converging nozzle. And getting that turbulence at the particle scale right is important. And we just don't have models that exist. And so if I had an Exascale computer, what I would love to do is essentially what we're starting to do now are these particle resolve simulations. You directly solve conservation of mass, momentum, and energy, use some type of either inverse boundary method or some technique to apply the boundary conditions at the surface of each particle. We can do a couple hundred particles right now. The challenge is, unlike in incompressible flows, as you increase that Mach number, you get these shocklets that form. And so the resolution requirement gets even stronger. And so with an Exascale computer, being able to do those types of simulations under relevant conditions, finite Mach number, Reynolds number, volume fraction, particle resolved at very large scale, would really allow us to look at that microscale physics. Look at improving those drag laws and the subgrid scale velocity fluctuations.
Great. Thank you very much. A more general question is, do you think the CFD community and your and our community, you think, are we ready for exascale computing, or you think?
I get cynical about when I hear Exascale, because I rarely see simulations with 1 million cores. I mean, people do it, but it's often it's sort of a proof of concept.
Yes,
I think there's a number of challenges, right? I think the fault tolerance, right? As you go towards Exascale, you have more and more processors. There's just a higher likelihood that you'll have processors fail. And so we have to reconcile that. The other thing is the amount of data being generated. I don't think, we have to think very carefully about how we post-process and visualize data. And so I think we'll really need to take seriously this idea of on-the-fly visualization, right? And I know there's some work in that area, but we can't just dump data every 100 time steps and then come in later and try to post-process it. It's just too big. And then on top of that, how do you share the data as well? And so it's sort of adopt smarter ways of storing data in databases where maybe all the data is on the database, but users can access portions of that data. And there's a huge center here at Michigan, not related to fluid dynamics, but they are really addressing that. How do you share very large amounts of data between communities in smart ways? So I think we need to figure that out. But I do see a lot of interesting developments. This idea of adaptive, so locally changing the precision, so going from double precision to single precision in a framework like DG, where it's sort of straightforward to do that, or at least change the order of accuracy as well locally. I think is very promising, and there's a lot of interesting developments there to think about going towards Exascale. I would. I think incompressible turbulent flows, either spectral methods or finite volume, works pretty well. And I think there's a lot of, maybe there's challenges with scaling FFTs, but I think a lot of those methods and algorithms are pretty mature. But like I said before, I think for compressible turbulence, it's very much still an open question. What direction are we going to go? High order finite volume, which becomes very expensive very quickly. DG, which has very nice scaling and properties, and very nice high order. The locality of it makes it so it scales very well, but it has its own challenges. So that's less obvious. So I think there's a couple things that need to be figured out. But I imagine, and then obviously with incompressible flows, you have the pressure Poisson equation. So then you have solving large linear systems. So it's not obvious to me. I think there's definitely some things that need to get figured out, but I think there's been steady progression. You know, I think there's been evidence that we're definitely moving towards that direction. So
Great.
that's my way of saying I don't know.
That's very good. And do you think you are going to stick with Fortran and MPI, or you think at some point you will have to rethink your strategy with your solvers?
Yeah, it's a good question. At the moment, it's I'm happy to continue using it because it's still being supported and it still works well. You know, when I was at the University of Illinois, I was in this big center. It was actually the Center for Exascale Computing of Plasma Coupled Combustion, and so Bill Gropp, who's one of the creators of MPI, was one of the PIs, and so that for a fluid dynamicist who usually lives in a mechanical engineering department to work with those computer scientists was pretty eye-opening. And there's a lot of interesting developments on MPI, you know, going towards adaptive MPI techniques to where you overprescribe the number of processors, and then you transfer the data. If a certain processor is heating up, it'll just transfer the data over. So I think, you know, standard sort of vanilla MPI, maybe we'll move away from that, but I don't know necessarily we're going to move away from MPI itself, because I know there's a lot of interesting developments in that area. But yeah, it's I don't know. I guess that's what I have for that.
Good. Well, I'm in the same situation as you. I have Fortran MPI code, and it's unclear what to do. Anyway, I have one last question for you. So we are talking a lot these days about exascale computing, but what do you think is going to happen after that? I mean, in 20, 30 years, do you think we are going to have like a revolution with completely new hardware, or do you think it's just going to be more cores, more powerful, more efficient? What do you think will happen eventually?
I don't think we can continue sort of this Moore's law. You know, we're at a point where you need like a nuclear power plant to power these computers, right? So we have to reconcile or address the energy consumption problem, which will probably happen. I really see this idea of running a big simulation, a single simulation, and trying to extract physics. That's useful, especially for academics. But in industry and in, you know, a lot of applications, you really want to improve a design or optimize something, and that requires running many simulations. And so we're seeing advancements in a number of different areas, right? So adjoint methods, for example, you run your calculation, then you do an inverse calculation. So your cost is about 3 times that of the forward run, but now you get sensitivity information that you can use in gradient-based optimization. That's had huge success in the aerospace industry, you know, for shape optimization, and we're starting to see it more and more for other applications. So my group's using it for trying to optimize mixing and for turbulent combustion. And so I think techniques like that, also obviously with machine learning and so forth, to go beyond a single prediction, right, and try to use it for design optimization, I think we'll see more of. And I think again that, and also uncertainty quantification at the same time. So these are applications where you have to run many simulations simultaneously, and that I think would be promising for these very large scale simulations, and not necessarily running a higher Reynolds number with number of grid points, but running many simulations and improving design, which we see a lot of success with RANs, you know, especially in 2D today, but it would be awesome to look at a 3D turbulent flow and find the optimal solutions for that. And so that's one area. And I think there's, you know, on the fly sort of just-in-time compilation, you know, really integrating software with the hardwares, you know. At first, the question was, are our GPU is going to stay around? And now everything is heterogeneous, you know, XPUs, you know, it's you know, we know that most likely the hardware is going to get more heterogeneous. And so having software that more and more integrates with that, and in a way that is usable by, you know, someone like you or me who writes code to solve fluid dynamics problems, we don't have the bandwidth to also know about how do we compile on each individual machine. So that means, compiling in a smart way where we have these specific kernels that do the physics, and then we have another infrastructure that tries to say, okay, this is the best way to build it on this particular machine. There's nice efforts in that area now, and I think that's going to be more and more useful.
Great. Thank you very much, Jesse. It was very nice talking to you. And we, of course, wish you all the best for your future endeavors. I can see you are extremely, extremely busy with NASA and with the COVID-19 pandemic. So best of luck for your future research.
Yeah, thanks for having me. It's always fun, talking about fluid dynamics and high performance computing. So I really enjoyed it.
Good, thank you. So thank you everyone for listening to this podcast. As usual, you can find all the podcasts available on the UK Turbulence Consortium website. Just Google UK Turbulence in one word, and all the links will also be posted on Twitter. And once again, it's the same at UK Turbulence. You will find all the links on YouTube and SoundCloud. So thank you very much, everyone. And hopefully I will see you soon in a new episode of the podcast. Bye-bye, Jess.